So we have Priscilla Pessi from NCBJ.
Yeah, the name of the institute is in Polish, so I cannot say it. Yeah, I'm Priscilla. I'm a assistant professor slash postdoc at NCBJ, which is in English National Center for Nuclear Research in Warsaw. Today I will be talking about the elephant pipeline. But first, I would like to thank the organizer for giving me the opportunity to talk about this pipeline that I very much like for how it came to be. I cannot tell you the whole story because it's very long and I don't have enough time to. But basically what the pipeline does is try to identify hostless transients in real-time alert stream. Okay, so we are all familiar how an alert stamp looks like. So usually we have the transient associated to a host galaxy. I'm talking about extragalactic transients. But there are some others that look like this. So we have an extragalactic transient that in the template stamp shows nothing. So no host galaxy. Does it mean that the host galaxy is not there? Well, probably not. Probably the host galaxy is there and is fainter than the detection limit of the telescope. Does it mean that this particular transient is a hostless transient? Well, no, but it is a hostless candidate. Are there truly hostless transients? Yes, there are. So how many are there and what can we say about them? Well, we don't know because we are not collecting samples systematically. So this is what our pipeline tries to do. The motivation of the pipeline has changed a lot through time, but I think now this is a good thing to try to understand what are the events that we have been flagging over time. So the pipeline is very simple. We develop it within the Think broker. So basically, we use all the capabilities of Think to only collect alerts from extragalactic transients. And then, of course, we develop this with CTF. So we have the science and templates of extragalactic transients, and we have many. So we stack them to increase the quality of the stamps. And so we sigma clip the stamps. And if we find an extended source in the sigma clipping, then we say, okay, there is a galaxy here, and we discard the event. And if there is no host galaxy in the sigma clipping, we say, okay, are we sure this is hostless? Well, we don't know, so let's study the Fourier transform. So we convert the template into a Fourier space, and we analyze the power spectrum, and then we shuffle the pixels in the template, and we do this again, and we shuffle again, and we do this again. And then we measure the distances between the distributions, and then if the distances are, if the distribution between the unshuffled template and the shuffled template are on top of each other, we say, okay, we are not shuffling anything else than noise. So this event is hostless, and if the distributions are different, are separated, then we say, okay, there is something else there. There is some other signal, and so there is a host. Okay, so in practice, it looks like this. So here you have a typical event with a host detection. So in the top part, you can see the stamps, and in the bottom, you see the sigma clip stamp. And here on the left-hand side, you can see that in both cases, we see a very extended source in the sigma clip stamps. And so we say, okay, this is the host, and so we discard it. And then on the right-hand side, yes, we see that we have an event without a big source in the sigma clip stamps. And so we proceed to the power spectrum analysis, which basically looks like this. So in the top here, I included an event that has a host. So typically, we wouldn't do this for things that have a host because it would be discarded already in the sigma clip, but we need to show how it works. So in the top, you see the template and then the mask, so the sigma clip stamp that we fill with noise, so it is smooth. And then we do this shuffling, and then we analyze the distances between the distribution, and you can see here that the distribution is separated, and which is different than what we see here in the bottom, where the distances are on top of each other. So we say, okay, this event is a hostless candidate. Okay, so what have we found so far? Well, we have found many things, and we are trying also to characterize our pipeline. And this is the work led by Rupesh Durgesh, who is also looking for a PhD position. So if you want someone that is highly skilled in dealing with alerts, let me know. I will tell him to apply. So on between the start of this project in 2023 and December 2025, our pipeline flagged 877 events, and 276 of these have a classification on TNS. So unfortunately, we have a ton of 1A supernova, and I say unfortunately because I'm purple supernova, and I was not looking for this. It was a bad overlook of my side. But we also have many other interesting stuff. We have superluminous supernova, which were the things I was looking for. And we have even some TDE. We do get a lot of CVs, which are our major contamination source. But well, we are doing this analysis now, that is a work in progress, to try to understand how good our pipeline is. So the other thing that we did is to cross-match with different catalogs. Think does some cross-matching, but it doesn't include all the catalogs. So we decided, okay, now that we have our sample, let's do a cross-match with the catalogs that Think was not currently considering. And so we use two different codes. We use the Lasser's Sherlock system and Prost that was mentioned earlier today. We noticed that both codes find different amounts of associated host galaxies, which I think is cool to know that, okay, it's good to do things differently because you get different results. And then you can see that this cross-matching flagged a lot of galaxies. So a lot of the things that we flagged actually have a host in a catalog. Does it mean that our pipeline doesn't work? Well, I don't think so, because you can see the majority of the found hosts for our flag hostless candidates are dimmer than the limiting magnitude of CTF in the R band. So you can see this red dashed line here is the CTF limiting magnitude. And you can see that most of our things are way fainter. We do have some brighter hosts that we are trying to understand. And we find many interesting things. So again, this is work in progress, but I will show you the sample of type 1 superluminous supernova that don't have an associated host. So they were flagged, and then they were cross-matched, and then we also did some eyeballing. So we visually look at the stumps of these events, and we found no host. And the most interesting event, I think, is this CTF 25AAOFTTV. I'm reading it because who can't remember this, but okay. So that has a peak absolute magnitude of around -23. That is very luminous for a superluminous. So it's cool that we catch it. We didn't follow it up, but I think it's a very interesting object. It's classified, so it has a spectroscopic classification. So hopefully someone follow it up, because it's among the most luminous events. Okay, so then we proceed to implement this on the LSST real-time alert stream. We have two main issues. One that was already there for CTF that were high proper motion. Oh, what did I do? Okay, that were high proper motion stars. Okay. Okay, I think I know what it is. Okay, so again, high proper motion stars were sometimes badly flagged on CTF. And then on LSST, we saw that we have a lot of solar system objects. We were processing on our own version of the pipeline. And there was something with the flagging of solar system objects. And then suddenly we have a ton of them. And we don't want them because we want extragalactic things. But what we noticed is that the coordinate distribution of these high proper motion stars and the solar system object is basically a straight line. And so we say, okay, if we just fit a straight line into the coordinate distribution and the fit is good, then we can say this is an event that is moving, and so we can discard it. Because usually for transient, you just get a little cloud of coordinate dispersion. So we did this. This is not yet implemented in the broker, but there is a pull request, so it's going to be implemented soon. So basically, it does that. A polynomial fit into the coordinate dispersion, and then if it is a line, then we say, okay, we don't care about this. We did find many interesting things, three, on the LSST alert stream. So one of these we even discovered. So 2025 ALTT we discovered with our pipeline. And Interestingly enough, these three were, well, two of them were spectroscopically classified as superluminous supernova, and the other one was identified as a potential superluminous supernova with the super hot core. So I think for us, this was a proof that, okay, we were able to improve our pipeline, and now we are flagging even more interesting things than before. We are not going to report these events on Astronaut anymore because of various reasons, but that we can discuss. But this pipeline is working on the Think broker. So if you are interested in the candidates that we flagged, you can always go to the broker and check them out. So this is summary. I think I talked too fast. So in the morning, we were listening a lot, or we heard a lot about how important it is to have the host to be able to characterize the transients. But okay, we have a lot of transients that don't have an associated host, or at least not one that we can see. So it is interesting that we can do a very simple pipeline that can tell us which are these events, and we can study them further. Our pipeline is simple. It provides maximum scientific return with minimal information. Basically, we use the aggregated information in the broker and the stamps, and we don't use anything else. Well, now we included a linear fit to the coordinates to try to discard things that were moving. But yeah, the techniques that we use are fairly simple. For a long time, we were claiming that our techniques were completely transferable to other alert streams, and now we have proven so, because now this pipeline is running in the LSST alert stream. So as long as there is a template and science cutout, we can find these events, and of course, we can also do it with Roman. And you can tell me, okay, why do I care? I could just do a catalog cross match, right? And then just take the ones that don't show a catalog cross match. But for us, it's okay, yes, you can do that. But for us, it's more than that, because there are a lot of galaxies that are also not cataloged, right? So everything that we find that has a galaxy, we don't care whether it's cataloged or not. And this is important when we go for deeper and deeper observations. So something that is not visible in CTF is visible in LSST and so on. So yeah, I was asked for a discussion topic, and this is a discussion topic, so I will leave it there.
For questions, over there.
Thanks. Thank you. Do you have a histogram plot that is normalized by rates, like the intrinsic rate of each supernova type? And does it look like how?
No, we
Okay.
don't. Okay, but this is, we can do that.
Yeah, I'd be interested to know like where,
Yeah.
like how superluminous supernova changed in that histogram.
Yeah.
He was first. Done. Yes.
Okay, so my question is, do you find any examples of very nearby low redshift hostless transient?
Yes, so this is, so I show you that there were some hosts that were very bright, and then we are detecting as hostless, and it's because the host expand the whole stamp. So if the host cover the whole stamp, then we do the shuffling. We are shuffling the host around, and it's like we say, okay, we are shuffling the background. So in this case, our background is the host. So if things are very nearby, and then the host occupies the whole stamp, then we are flagging them as hostless when they are not.
Okay, so did you find any true example of hostless
very nearby? No.
Yes. Okay.
No.
Thank you.
See over there. I just have a very quick question. Are you still submitting to TNS, but just not as astronauts as discovery reports, or are you not submitting anything at all?
Okay, so we had a discussion about this, about submitting at least or the discoveries or something like this. But then we were not understanding how much the community was actually considering this. And also we were thinking, okay, when the actual survey starts, then having a ton of discoveries, I don't know if it adds a lot. Maybe like having too much information can also be having noise. So we don't want to add noise. I think we may evaluate to send the discoveries, but the astronauts, we were thinking, okay, maybe we are just creating more noise, and I don't know how much it's used.
Just as a personal opinion, I feel like, I mean, I don't know what this will look like, but I think that TNS can be useful as like vetted candidates and kind of a step beyond maybe like what an initial filter would give or something. So I still see like that it could be valuable in addition to kind of whatever is on the brokers.
Okay,
Thank you.
Okay, we should move on. Let's thank Priscilla again